So I will begin with the notion of a discrete dynamical system. So what are dynamical systems? You usually have some space called the configuration space, and on this configuration space you have some starting point, and then this point somehow evolves along the configuration space following some vector field that you can think of as a first-order differential equation, or a system of first-order differential equations. Then, if you want to discretize, you can say, well, let's just take locations of this point at time intervals of epsilon, and you have a sequence of points running here. So, for discrete, you assume that there's no trajectory really. You just have a sequence of points. So this is a discrete dynamical system. Somehow points move around, right? So you think about them as xn minus 1, xn, xn plus 1, and there is some kind of a rule how these points move. So I will call this a configuration space as x. So this is my configuration space. And in order to define the dynamics, I have some function f that sends my x point xn to the point xn plus 1. So I need to have some function f from the configuration space to itself, right? And then I iterate the function, and that gives me my dynamics. Of course, if you draw something like this, it's hard to see the dynamics because all your points are on the same space. So what you can then do is you look at your time axis, you look at the extended phase space, your time axis, but your time here is not continuous as an integer. So really, I drew the line for convenience, but I'm thinking only about isolated times. So here is my configuration space x, and here is my starting point x naught, and then this would be x, and then this is my point x1, and so on. So here is my x n minus 1, xn, xn plus 1. In this subject, there is a notation. The notation is xn we usually denote by x, and xn plus 1 we denote by x bar, and xn minus 1 we denote by x underbar. So that's sort of a tradition. Okay, and I go by the function f. Okay, so then my xn is f composed with itself n times from this one. Okay, so this is an example of what is called autonomous discrete integrable system, a discrete dynamical system. But nothing prevents us from saying that, oh, let this f be f naught and let this f be f1 and change the function. Of course, you don't want to just do random changes of the function. What you think about is that your function f depends on the point and also depends on some parameters. Let me call them a. And so you want to make these parameters sort of depend on them. That's an example of a non-autonomous dynamical system. And if we go in this way, why not assume that the configuration spaces are also slowly varying with your time? Okay? So then what you end up with is something like this. You have a family. You have a family of configuration spaces that you can think of as like one big configuration space itself. And in this family of configuration spaces, you have this trajectories, but the rule for the function and the surface itself can vary. And that's what discrete Painlevé equations are. So families of these surfaces, I think, should be called Sakai surfaces, because he really explained what they are. And okay, yeah. So how can we construct something like this? So
base is Z.
Huh?
So Sakai surface that you set as a family is has a base.
That's
Z.
a trajectory. So base is not Z. Base space. Base space is this.
Family over.
So you can have a different trajectory going in different directions.
So the base space is given by the A's in particular, or those?
Yeah, base space is given by some
the moduli.
Yeah, some moduli. Right. So all this, again, I'm hand waving a little bit. I will clarify a lot of things. So I'm not saying don't ask questions, but don't expect answers. Okay? All right. So, and really, it starts with the simplest possible example of a configuration space. If you take configuration space to be aligned, that's probably a little bit too simple. So let's take configuration space to be a plane. Okay, so I'll take a plane. And I want to define some mapping from a plane to itself that I can iterate. And I want the mapping to be nice, because that's usually where we diverge with people doing interesting things like chaos, Mandelbrot sets, etc. They want chaos. We don't. We want integrability, conserved quantities, explicit formulas, algebraic structure. So I'll do the following. So here's a plane, and this plane has coordinates, let's say, x and y, okay? And I will write an equation of the following form. I'll write an equation of the form x squared x1, some 3 by 3 matrix A, y squared y1 equal to 0, okay? So this equation will define a curve, and let me call this curve gamma A, okay? It's quadratic in x, and it's quadratic in y, given by 2 polynomial. So we can draw it. Trust me that it will look something like this generically. So you have a curve that looks like this. And on this curve, you can define two natural dynamics. First dynamic is, it's next to obvious. So pick up a point, right? Because the curve is quadratic in y, if I fix x, there are 2 points that have the same x. And the dynamic would be ry. It's an involution that switches these 2 points. Okay? Now, if you know a little bit about affine Weyl groups, you would go like, oh, involution. But you don't have to. Okay? Now, and you can do the same thing in the other direction, right? So fix the value of y and interchange the values of x. So you have here x. That's another involution. Okay? So both are boring because they're order 2 maps, so you don't really have the dynamics. But then you do the obvious thing. You say, oh, let me do ry and then do rx. And then I say that this is my starting point xy, and this is my new point x bar y bar. Okay? And you start iterating. And as you start iterating, this point will, how did I manage this? Okay? This point will do a tiny jump that you can see here, and then jump here, and then you see that there will be some kind of a motion on this curve. Nice, interesting motion, very regular. Okay? Now, I am surprised that no one asked me about which plane. I guess my warning that don't expect answers was effective. But let's think about this.
I was actually going to ask you that so you said degree 2, but this looks like a 2-2 curve in P1 cross P1.
Why did I even? Okay, so what do I want? I want that I always have two roots to a quadratic equation, right? That puts my plane into complex numbers to be C cross C, right? And what Randza is saying is this is not a single equation. It really is a family of equations parameterized by this matrix A. And if you have a family of quadratic equations, for example, your leading coefficient can disappear and your quadratic equation will become linear. That would be trouble. So how to deal with that? You introduce homogeneous coordinates on P1 cross P1, and then disappearing solution just becomes a point at infinity. Okay? So that's why this is indeed P1C cross P1C. That's what my plane is. Okay? And this is a bi-degree 2-2 curve in P1 cross P1. Okay? And given that all of you are algebraic geometers, or aspiring algebraic geometers, or know algebraic geometry, you can tell me how would the generic biquadratic curve would look like? Since you started this.
How would it look like? Like that, right?
No. I mean, if you think about complex algebraic curve of pi degree 2-2.
Wait,
It's not a
it's
parenthesis on the
genus
spot.
1 curve,
Everyone
right?
can answer.
It's a genus 1 curve, right?
It's an elliptic curve.
Yeah, it's an elliptic curve.
So this is an elliptic curve. Generically, this is an elliptic curve. You can think about it as a model on the parallelogram. And turns out that this dynamics is, of course, nothing but a shift in some vector in the abelian group structure on this curve, and that's how you run around. Okay? That's one remark. There's another remark. If you think about P1 cross P1, right? So what is this topologically? So P1C is just a Riemann sphere. So this is like S2 cross S2, right? So it's a sphere.
It's sorry.
Yeah?
Sorry, I'm 30 seconds behind you, but what you just said, it's just a linear equivalence, right? Because you have a vertical line, a horizontal line, each gives you a divisor, and then you cancel one, and is that right? Sorry, ignore me.
I'll ignore you. I don't think it is.
It's not. Okay.
And in any case, that's really not
what this is about.
What
right?
this is about. So let me not pretend that I know more than I do. I still think. So this is this thing, right? So if I look at second homology or cohomology, right? Doesn't really matter. Let's do homology. Right? What would that be? That would be a rank 2, right? Group with these two generators. So it's isomorphic to H1 on P1 cross P1 on star, right? And this is known as a Picard group or Picard lattice of P1 cross P1. Okay? And in here, so this is integer span, and the generators, if you think about P1 cross P1, this is the diagram that I would always draw for P1 cross P1. So this is my like x equals to 0, y equals to 0, but this is x equals infinity, y is infinity, y is 0, sorry. This is y is infinity, so on. Okay? So on P1 cross P1, they're very natural hypersurfaces or curves. There's a vertical curve, and there's a horizontal curve. Vertical curve we get by fixing the value of x. So I can write it hyper curve. X is A, right? Something like this. And this one, I'll write H, Y is B, for example. But really, that's your linear equivalence.
Yeah.
You can move this around, right? So A is not really important. I can just call it hx. And if I take the class of hx, that will be the class of one of those spheres. I call classes to be curly hx. So this would be hx, and in the same way, we will have hy. Okay? So, and also, this comes equipped with the intersection product. So hx dot hy is equal to 1, right? How do you show something like this? These are equivalence classes. So to compute something on equivalence classes, you define it on representatives and show it's well defined. So you take two lines, you see they intersect at the point, that's why. Now, what about hx dot hx? Well, you take two representatives. Well, you don't want to take the same representative because they don't intersect transversely. So you take two different representatives, but then they don't intersect. Okay? So you have this thing. Okay? And I will be going between homology and cohomology, but really thinking about it like this. Okay. So this is the Picard lattice of P1 cross P1. And the reason I'm bringing this up is there is something known as a canonical class in this lattice, right? So we have K P1 cross P1, okay? That we can express in terms of generators hx and hy. How do we do that? Because it's a surface, we take a top form. So we take omega is some function f of xy dx which dy, right? For simplicity, let's assume that there is no function here, just dx which dy. So this form has no zeros, has no poles, right? But this is the computation in the little x, little y chart, okay? So if we change it to the big X, which is 1 over little x, and also big Y, which is 1 over little y, this form will become dx which dy over x squared y squared. So you see that this one is has poles of order 2 along the two lines at infinity that I just erased. Okay? And if you put here a function, you can move these lines. It's actually more convenient to put the function in the denominator. Okay? Then this function will transform in the following way. So if you switch coordinates, it will transform as 1 over big X, 1 over big Y, multiplied by this x squared, y squared. But that's exactly how the curves of by degree 2, 2 transform when you think about them in terms of homogeneous coordinates on P1 cross P1. Okay? So really, when I'm thinking about this gamma A, and if I take the class of gamma A, the class of gamma A would be, I'm sorry, I didn't define the canonical class. So I take a divisor of omega and then I take a class of it, and this is what is called the canonical class. So really, my biquadratic curves gammas are sections of the anti-canonical line bundle. Okay? So far so good? So, and this minus kx would be 2hx plus 2hy, right? And canonical one would be minus 2hx minus 2hy because of these two poles. Right? Okay. Right. Let me get back to easy pictures because I feel that I flew off a little bit. So you see, I have a beautiful dynamical system on this curve. Reversible, having algebraic structure, but I really wanted to do it on the plane, not on the curve. So I want to be able to tell you where this point goes, where this point goes, where this point goes. Okay? Using that very same construction. So what to do? And the answer is very simple. Try to somehow foliate the plane by two curves. For that, you do the following. So I have this curve gamma A, determined by the matrix A. So, and I'll just write it as X transpose AY equals to 0. And then I take another matrix B and take the curve gamma B, X transpose BY is equal to 0. And take their linear combination. Take their linear combination. So it would be lambda naught X transpose AY plus lambda 1 X transpose BY is equal to 0. So this gives me a one-dimensional family. So this is a P1, where P1 is this pair lambda 0, lambda 1 up to proportionality family. And such a family is called a pencil of two curves that are, of course, still in the same class. Okay, so do I have blue color? Yeah. Okay. So let me maybe do this and do this. So my phone's still distracting me. Okay, so this is my A curve. Okay, and here's my B curve. This is a schematic picture, okay? So it may look like it has vertical line crossing it at 3 points, but it doesn't. That's the best I can do. Okay? Then, any point here, I can find some other curve. So this is gamma lambda, and this is gamma B. This is gamma A. Okay? So it's a very easy statement that given a point, I can choose parameters lambda 0 and lambda 1 to have a curve from this family going through this point. Essentially evaluate these two equations at the point and flip with the sign. Do you see what the problem is? Where can things go wrong? So suppose I start, let's say somewhere here, right? Then what do? Or maybe start somewhere here. I go here, and then I go here, right? And it is possible that I may land at this point.
On green or on blue?
That's the problem.
Ah.
On both.
Oh, nice.
Because, so I start on my green curve, right?
Yeah.
And it's like, it's a unique curve going through this point. I'm happy, I'm like, I'm green. I'm going to another green, right? And then if I ended up here, I'm lost. Because there are two curves. Like, should I follow the green road or should I follow the blue road? It's actually much worse. It's much worse because for these points, what does it mean that gamma A goes through this point? That this is 0, right? What does it mean that gamma B goes through this point? That this is 0. But then this whole thing is 0. So it's not two curves that go. It's all curves that go through this point. Okay? What does it mean mathematically? It means that homework exercise, write down equations giving this dynamics. Okay? And what happens is this equation stops being defined. You have rational mapping, so if you have 0 over 1, you know what it is, it's 0. If you have 1 over 0, you know what it is, it's infinity because we're in the projective case. If you have 0 over 0, that's where you don't know which road to follow. Okay? Easy question. How many points did I draw?
8.
8. Why is this accurate? Generically.
Okay.
Well, I didn't. What was the correct? Yes.
Y8.
Why is 8 the right answer?
Why is 8 the right
Because
answer?
intersection numbers.
Yeah, because you are in 2hx plus 2hy,
Yeah.
you square it, you get 8. So you have 8 base points, okay? So, in a sense, Sakai classification is a classification of 8 points in the plane. That's all there is.
A classification of 8 points, you're saying?
No, classification of discrete Painlevé equations is essentially classification of 8 points in the plane, and I'll explain.
That's why E8 has 8 there?
Well, E8 affine has 9, and in fact it's 10, but 8, and did I promise not to answer questions? Okay, so we have this, okay? And here comes the beautiful idea, and the beautiful idea is, as usual, we have a mapping. The mapping develops a singularity. How do we fix the singularity? We do some local surgery. We adjust the space on which the dynamics is to take care of this singularity. Okay? So let's see what's happening at this point. There's a blue curve going in, green, black, but they all come at different slopes, at least the way I drew the picture. But the way I drew the picture is conceptually correct. So if I want to keep track of my green line, I should keep track of the slope with which it entered, right? So, and of course, that's exactly what we talk about when we talk about the blow up, right? So what is the blow up? Locally, blow up is the following construction, with apologies to algebraic geometers for oversimplifying it ridiculously. You have a point here, and you add one extra dimension. So here you have the dimensions, the coordinates x, y, and you here add the dimension of a slope. Slope and slope k. Okay? So then over this point you have a line of all possible slopes. And if you want to take into account both horizontal and vertical lines, of course, this is again P1, right? This is like a definition, right? P1 is the space of lines going from the origin on the plane. So then, if I have my green line, I mark its slope, and I sort of say, oh, okay, it actually goes through this point. And if I have my blue line, I mark its slope, and say it actually goes through this point. You can do it carefully in coordinates, but I don't want to write that. If you've seen that, you know. If you haven't seen it, if I write it here, it wouldn't help. But it's pretty straightforward. It's how it looks, okay? Then there are some notations that are important.
Let me maybe say for people that haven't seen it before, that the punchline of what you're saying is that whatever he did upstairs is a surface which is almost ever the same as the plane. It's just kind of twisted in some way, but it has this additional line that parameterizes the tangent direction to those unique points, right? So it's a sort of a surgery where you replace this point with a line, and so you get more information about the infinitesimal direction of this point. But it's a surgery that's so well done that it's a nice smooth surface upstairs.
It's bijective away from the center.
Yeah.
So okay. So you have this projection map, and suppose this is your curve L here, okay? It's natural to denote by L the preimage of the curve L under this map. And if you do that, you will get this green line together with the all of the big central fiber. So the way you go around it, you call this E, and then you say that just this line, which you get in the following way. You cut the point out, and then you fill in by closure. This line is called the proper transform under the blow-up. This is L minus E. Okay? All right. So we have that. Another thing that happens when you do the blow-up, as Ramsey said, we're doing a surgery. And the way you think about the surgery is, this is the point of a blow-up, and what you do is you sort of blow a bubble here, because this is what you just did. P1C is just a sphere. So in particular, in this cohomology, you start adding classes PIs of these spheres, and the rank of your cohomology is growing. Okay? Another thing is, you can talk about the intersection. So you need to be able to say how intersection works here. And that's where people start losing interest. Because you're saying that, oh, it intersects with itself -1 times. Okay? So what happens is you should not take this literally. It's one of those, like, correct me if I'm wrong, 1 + 2 + 3 + 4 is -112, right?
Jamie is the best. Yeah. Okay.
Yeah. It doesn't make sense, but you can make sense of it by saying, well, look, we think about this in this way, and then it makes sense later on. So what's happening here is, how do you compute the square? You take two representatives, but your representatives, you want them to be transversal, okay? So when you were doing it for the plane, it's good that the screen is there, right?
Yes.
Still just in time.
We've had many speakers like lunge towards the smartboard with a marker, and everybody back.
Okay, this is my vertical line HX, right? How did I move to a parallel line? I said, oh, this is a normal bundle of an embedding of this line in the projective plane. It has a section. This section is my parallel shift. I'm good. I try to do a normal line, normal bundle here, and that one is twisted. It has a term class of -1, and that's exactly the meaning of this self-intersection. Okay? And then every time you blow up, the self-intersection of this line decreases by 1. So if this was like HX, HX minus E would have a self-intersection of -1. Okay? So, yeah. So this is what I will do. I will blow up these 8 points. I blow up these 8 points, and I get a surface X. Okay? That is a blow up. Blow up, and P1 to P9, or P8 rather, of P1 cross P1. This is my surface, and that surface is really very special. So maybe I'll erase most of this. So here's my surface X. There is this blow-up map to P1 cross P1. So what I had here was a fibration by generically elliptic curves that failed to be a fibration at this point. But now I separated everything. So I have a genuine fibration by elliptic curves. So I have my tori sitting here. And I have my dynamics now stays on this tori. Okay? And this tori are coming from the family. This is, so, I don't know how to do this. Let me, these are curly braces. So this is a lambda 0, lambda 1 family.
So that blue fiber is over.
Like it's one of those, and then this is the other.
Why is why is elliptic?
Well, because generically any biquadratic curve is elliptic. Any 2-2 curve that I start with.
So that fiber is over a point on the
No. The fiber. So it's not a fiber. It's not a fiber. It's just the foliation. Maybe that's a better word. So I have my blue curve here,
Yeah, for
and I
gamma
lift it,
B.
and now it's
Properties, you draw the
yeah,
properties.
yeah, proper transforms
Also
of these
transforms.
curves. Now, about the fiber, so this is a family, and this family is parameterized by the parameter of the pencil. So this surface has a projection to this P1C. Okay? And the fiber of this projection is one of those. So it's a fiber in that sense.
Okay.
So it's a proper transform here, and a fiber here, right?
So it's if your colorful curve where it's kind of squiggly horizontal, that would be a.
And I can't even argue with this, right? So, this is my P1C family, right? So for some value of the parameter, I have this elliptic fiber.
Yeah.
This is what you want? Obvious, right? So this is this elliptic fiber. So what do we have? We have a surface that is, on one hand, a blow up from P1 cross P1. So such a surface is called a rational surface because it's birationally equivalent to the projective plane. And I'm using P1 cross P1 because I like to do dynamics, but of course P1 cross P1 is birationally equivalent to P2. Okay, and also this surface has an elliptic fibration. Such surfaces are called elliptic surfaces. So you have a rational elliptic surface. Why is it in the family? Because, no, sorry, take it back. Not in the family, this is just an isolated representative. Okay? And it is well known that if you have rational elliptic surface, okay, the fibers that I drew are regular fibers, okay? And you can also have singular fibers. So one way to think about a singular fiber is you have your elliptic curve, and suppose that you pinch one of the cycles. Then you get something like this. But suppose you can also pinch the other cycle, so you get fibers like this. So you can think about these fibers as some kind of configuration of rational curves or spheres are connected in some way, either as a node, as a cusp, or as a bunch of components. Okay? So I have one example. So one example. Look up. So it's a very famous example. So you take the matrix A, that is 0, 0, 0, 0, 1, 0, 0, 0, 0. So if you think about the curve gamma A, it would look weird, because what happens is you have local equation of this curve to be given by like x, y is 0, right? But this is when you think in terms of affine chart, and you have to remember that this is a biquadratic curve. So if you write it in homogeneous coordinates, it would be x0, x1, y0, y1 equal to 0. So that curve is actually nothing but a coordinate cross like this in the P1 cross P1. And if I take my second matrix B, matrix B would be 1, say alpha 1, alpha 0, minus alpha 1, minus alpha 1, and alpha is A plus 1 over A, and A is not equal to 0 plus minus 1, okay, then turns out that the curve corresponding to this matrix will look something like this. It will have two components that roughly go like, how did I? It roughly goes like this. Okay? So the base points that you're getting would be these base points. There are a few more intersections, but I don't mean that. Okay? So there are no tails here. Okay? So get this picture. Then the dynamics that I described for you, this dynamics that was R x following Ry, let me call this eta. This dynamics has a name. It is called a QRT map. Okay, QRT is for Quispe-Roberts-Thompson. So, because you have Rx and Ry, you can actually rewrite that as sigma Rx, sigma Ry, where sigma is just a flip of the x and y axis. I'm sorry, sigma Ry is where sigma just interchanges x and y. So instead of doing vertical flip and horizontal flip, I do vertical flip, switch coordinate axis, do another vertical flip, and switch coordinate axis back. Okay? This unfortunately also transposes the matrices. So if your matrices are symmetric, you have something that is called a symmetric QRT map, and it's nicer. If it's not symmetric, you need to be a little bit more careful. But you can call this phi, and this phi is known as a half QRT. This phi is known as half QRT. So there's a formula for it. So phi is the following map. X goes to x minus a inverse, y, x plus a inverse, and y goes to x. And you can immediately see the location of some base points. For example, when y is 0 and x is a, you get this point because your mapping is 0 over 0. You can, as an exercise, write down your pencil, see that this is where they intersect, construct a map, etc. I don't have time for this, but to give you the idea. Okay? So this is called the QRT map. There are induced mappings. The induced mappings will be on peak of x with itself, right? Peak of x to peak of x. So there will be mappings induced either by phi or by eta, which is phi squared. So that's just how do you define these mappings? You take a generator, you take an equivalence class, pick an element in this equivalence class, map it, and take the equivalence class. So the result, you can compute the mapping on Picard lines. Okay, so this is known as a QRT map. And this surface you can think of as a QRT surface. And this QRT surface has this elliptic fibration that has regular fibers and has singular fibers. Like in my example, there are parameters. So let me erase that. So there are there is this my parameters lambda 0, lambda 1, okay? And generically, you have your elliptic fiber. But when you have a 0, for example, or infinity, I don't remember, you will have these two intersecting spheres. if you have infinity, you will have this for intersecting spheres. So these are singular fibers, and this is a regular fiber. Okay, so this are my coordinate lines, but again, they're spheres. So, how to go from here to Painlevé? What is discrete Painlevé? So, it's almost correct. So I'm oversimplifying a little. But suppose you take a biquadratic curve on P1 cross P1. How many parameters does it have? Well, it's defined by a 3 by 3 matrix of coefficients, right? Up to scaling. Meaning you have 8 parameters, right? And you want the curve to go through 8 points. So if you take 8 generic points, there is only one curve going through these 8 points. And I have a family. Why do I have a family? Because that's how I created my 8 points. I took 2 biquadratic curves and intersected. So those 8 points that appear, they're very, very special. So here's what you can do. You can take those points, and they leave sort of on all fibers in the family. And you can wiggle them a little bit. So, for example, what I can do is I can push these points, and the locations here are something like A inverse, A inverse, minus A inverse, minus A inverse. So these points are very special because they are parameterized by this parameter A that I use to construct my mapping. So I will wiggle it to here, for example. Okay? And just push them away, push them off. So if I have these points, if I label these points like P1, P2, P3, P4, P5, P6, P7, P8. So instead of having A here, instead of A, I will have some parameter B3, and so on. Okay? So then the following thing happens. First, your pencil is completely destroyed. You have a unique curve. And you sort of want to keep the same dynamics. This is difficult, I'm not going to explain how, but you can. So if you keep the same dynamics, what happens is your points are sort of slowly drifting on that cross that I chose. You were asking about the moduli. These are the moduli. Essentially, the locations of these points modulo the Möbius group actions on each of the coordinates. Okay? So that's how you get your family of surfaces. You are parameterized by the location of the blow-up points on that particular singular configuration. And your dynamics is shifting these points in some prescribed way. Okay? So in the remaining maybe 5 more minutes, let me explain sort of what is going on when that happens. So when first, if you look at peak of X, where you have this blow-up, 8 points, it is a rectangle lattice with coordinate classes and classes of these 8 bubbles that we create. Okay? In here, you have the anti-canonical divisor class. This is what my pencil was. And this is 2hx plus 2hy minus e1 minus e8. And before, there was a whole family of sections. Now there's no family. There exists, exists a unique anti-canonical divisor. Okay? And this anti-canonical divisor breaks into irreducible components. So if I have something like this, the irreducible components of the anti-canonical divisors turned out to be proper transforms of these four coordinate lines. So this minus kx would be hx minus e1 minus e2 plus hy minus e3 minus e4 plus hx minus e5 minus e6 plus hy minus e7 minus e8. Okay? So these are just these four irreducible components after the blow-up. And let me call them delta naught, delta d naught, d naught, d1, d2, and d3. Okay? And I can do the intersection diagrams for them. Okay? So the intersection diagram for them would be like this.
So minus kx, that upright letter, is a divisor or?
Is a divisor.
Not the
it's
class.
a unique divisor.
That defined from the class.
Right, but before I had a whole family of sections in that class. Now I have a unique section. So I have a unique anti-canonical divisor. And this unique anti-canonical divisor decomposes into irreducible components that is described by this diagram. This is linking diagram of type A31. So then this non-autonomous dynamic that we get is called difference Painlevé equation, Q Painlevé equation living on A31 surface. This is the surface type. This is the surface type. Okay? Now, I sort of told you that I am pushing my dynamics in a way that it's preserved. Of course, I don't mean the equations. I really mean the action on the Picard lattice. So I have some dynamics that creates the same action on the Picard lattice. But notice that in this Picard lattice, I got the following. I got the span of these classes, delta 0, delta 1, delta 2, delta 3, and we call this surface lattice. Okay? This surface lattice, actually, this is rank 10, and in this rank 10 lattice, there is an orthogonal complement of the anti-canonical divisor, and this one is the E81 type lattice. So this surface lattice is a sublattice of this E81 type lattice. And you can take another sublattice, which is spanned by alpha i's with the condition that alpha I is perpendicular to delta J. So you get another sublattice. It is also a sublattice in this E81 lattice, and in fact, the picture is something like this. So this is the anti-canonical divisor class, because it's 0 now. So this is the anti-canonical divisor class. Here is the surface, and here is the alphas. So this is known as a symmetry. Okay? So this is known as a symmetry sublattice. You can see that these alphas, they you can find the root basis in the lattice of alphas. You find the root basis, it will be given by this Dynkin diagram. This is the dual Dynkin diagram. To my A31, this is D51. Okay? And then here's the following beautiful thing that happens. So the moment you push your points away, you have this decomposition, and your surface type is determined by this anti-canonical divisor. And these roots are called symmetry roots, because if you look at reflections in the roots alpha I that act on various classes beta as beta plus alpha I dot beta alpha I, that's what happens to these reflection formulas. It fixes all your delta G, because alpha and delta are perpendicular. So in that sense, it's a symmetry on the level of cohomology. But even better, each of those can be constructed from maps from a surface with some parameter alpha to a surface with some parameter alpha bar. So what you do is you create a birational representation of your symmetry group that is sitting this W of D5(1), affine Weyl group sitting on that lattice on the family of surfaces. And in here, you have translation elements. And these translation elements are Painlevé dynamics. So that example that we had was a translation element that was permuting the deltas and shifting alphas. And so that's sort of where discrete Painlevé equations come from, like one way of seeing that. And just to wrap up, where is the 22 coming from? You start with an elliptic curve. And 8 points on this elliptic curve. You can do everything here, and you get a master equation known as elliptic difference Painlevé equation. You pinch. Wait, there are two ways to pinch, right? You can do a cusp, or you can do a node. So this is like the top equation in the multiplicative dynamics. This is a top equation in the additive dynamics. Then you pinch again. So you have like two spheres like this, and still your 8 points are scattered around somehow. Or here, you have two spheres like this. And basically, what you classify is you classify all possible degenerations of a generic family of 8 points into some kind of curve configurations. And that corresponds to classification of singular fibers by Kodaira. Of course, not all singular fibers you can realize on the same QRT map, but each of them can be realized. And that's how you get these 22 types of those lattices. And for each of them, you can construct a dual lattice. This dual lattice corresponds to affine Weyl group, extended affine Weyl group, but whatever. You can construct birational representation of this extended affine Weyl group. And then any translation element generates for you a discrete dynamical system. And turns out that these discrete dynamical systems, some of them have limits to differential Painlevé equations. That's where Painlevé equations come from, as far as I'm concerned, and I'll stop here.
Are there any questions?
Yes, now I answer questions.
I have a couple of questions. One is, so when you're saying take a curve with 8 points, are you saying that sort of like really the parameter space that somehow parameterizes this different type of discrete Painlevé equation is sort of the stratification of m bar 1/8 of the modular space of different point curves, or no? Is it,
I don't
no?
really think so.
Okay.
I mean, maybe, right? Because yes, you take an elliptic curve, and then you go into various boundary divisors.
Right.
So
But you don't know that like every different stratum that I could find MOA will give you something different. And vice versa, that if you move within one stratum, you're always going to get to the same system.
I don't know.
You don't
I sort of keep asking myself the same question, but partly I don't know why I should care. Aside from, yes, of course, moduli spaces of
yeah.
MGN bar, part of.
If you keep giving talks to algebraic geometers, you'll get asked that question all the time.
That's infinitely better than being asked about tau functions.
So, sorry, real quick. The second question I had, so the examples that you gave us had one fiber that was sort of the toric boundary of P1 cross P1, right? And that's sort of, it's not a generic case of a pencil of two curves,
but
right?
what happens is every pencil of two curves will have singular fibers.
Yeah, but generically, wouldn't it have like 12 one-nodal fibers?
Who cares about generic?
Well, I mean, I guess my question is like, does the
there-
generic
there-
situation give you a
there are lots of
particular
different-
system?
So there are lots of different QRT maps
Yeah.
that you can diatomize. I'm not interested in QRT maps, I'm really interested in discrete Painlevé.
Okay.
So QRT map that I spend 90% of time talking about is an excuse.
Mhm.
The real thing was that those last two blackboards that were impossible to follow.
So in particular, are you saying that the generic one does not give you an interesting Painlevé equation, or that
It gives you something.
something? Okay.
Part of the problem is it's actually not easy to write down the equations. So I'm saying, well, let's take a
I
birational
see.
representation,
So
construct birational representation, take translation element, decompose it in terms of generators, take their composition, you get the equation. Well, the problem is that if you have equations that are sitting sort of in this corner, your decomposition can be like 34 generators, each of which is a nightmare.
I see.
So you can't possibly compose them. On the other hand, this indirect approach allows you to write equations that correspond to this decomposition. So that's why QRT is kind of nice. Also, there's a parallel between, you have Painlevé equations, they have autonomous limits, like Gauss had the geometric, that have the solutions in terms of elliptic functions. So that's exact discrete parallel to that. But really, I think the hard part, if you start explaining what a discrete Painlevé equation is from the top, you're saying, well, let's take two dual linking diagrams in E81 and look at the anti-canonical divisor decomposing into this. Like people say, why are you doing this? How come? This at least gives you a motivation on where this is coming from. This biquadratic curves, these involutions. So it's sort of a nice path where you don't suspect that you're going towards the cliff. That was the last 10 minutes.
Yeah.
You just walk happy there. So that's like one of the reasons.
Sorry, what was delta I?
These are classes of components. Remember I had 8 points, so I push them somewhere. I choose
that's
one
really
of the curve of the pencil and push them. So if the curve is generic, like elliptic, there will be only one such delta. I have this elliptic curve, and if I take 8 points on this elliptic curve, then there will be no delta i's, there will be just one delta. Okay? On the other hand, if I take this singular fiber and push points along this singular fiber, this singular fiber has 4 components, and these deltas are their classes in cohomology, or homology. So this captures the information on what kind of type of geometry we have. That the type of geometry is you take like 4 lines and pairs of points on each of the 4 lines and blow up. And then vary the points, you get the family, and that's your configuration space. Shameless advertisement. I taught a class on that at BIMSA, where I pretty much explained all of that in a semester. So if you want details, you can search on BIMSA, bimsa.cn. There are videos and lecture notes, and there I go slower.
So maybe some general question. So making some differential equation to be like discrete, is that to solve in some sense, or I'm not like.
Well, I mean, there are a lot of motivation, right? There are some purely discrete models. So discrete equations, they can be thought of as capturing more information because you take continuous limits. So that's one interest. The other interest in discrete integrability is through construction of effective numerical algorithms, because if you have an integrable system, like say Hamiltonian system with conserved Hamiltonian, if you discretize it so that the conservation law holds, it results in the cancellation of error in numerical computations. So there are many motivations why people are interested in discrete. And this is like example of discrete integrability in the sense that like usual integrability is you have complicated nonlinear ODE or PDE, and you're able to construct infinitely many conserved quantities, exact solutions, etc. Usually there's some linear problem hiding somewhere, like the Lax pair that gives you all this. Okay, so this is an example of an algebraic structure. So the linear structure here is the linear mapping on the Picard lattice. So in fact, given the linear mapping on the Picard lattice, I can restore my equation completely, with the exception of if I have a particular initial condition, how does this trajectory behave? So I can restore dynamics, but not solutions. Although, similar to classical Painlevé for special parameter values, people obtain solutions in analogs of hypergeometric series, for example.
The last question.
Okay.
Anything you can tell us about the relationship between this Halphen and quantum cohomology?
Well, I say let's thank Anton, and then we can chat about this question. I don't know that I have any particular answer, but let's thank Anton again.